You need to allow me to.
Yeah, one moment, please.
We are waiting for the student. The student is. Good morning, Daniel. Good morning, Mark. Welcome.
Okay, Lourdes, ready.
Okay, you can start, teacher. Okay. Good morning.
Okay.
Good morning, teacher.
Good morning, guys.
Good morning, good morning.
Okay, so all right, so let us start. Okay, so today we will be doing these three things: equations and functions, and we'll see their basic definition and notations for both of them one by one. First, we'll see it for equations, the basic definitions and the notations, and then we'll see it for functions, basic definitions and notation, and then we will see the composite and the inverse functions, and at the end we will see about the transformation of the graphs. Okay, so all right, so let's start with the definition of equation. This is our first topic for the day. So this is our topic one. Okay, mathematically, an equation can be defined as a statement that supports the equality of two expressions which are connected by the equal sign. For example, 2x minus 5 equals to 13. So we have two expressions, one expression on the left side and one expression on the right side, and when both of these expressions are equal, we call it an equation. So here the 2x, okay, so the sign that connects these expressions this is the equality sign. So where we see this sign connecting the two expressions, we call that an equation. So okay, so let's say these are like the parts of an equation. Let's say I have just, for example, I have an equation 2x minus 5 equals to 13, as you could see. So now here this whole thing is a term. This whole thing is a term. Okay, this one also a term. These ones are terms. How we identify that it is a term? We identify it by looking at that where is the plus and the minus sign in between them. Like 2x, these are not two terms. This is one term because we don't see the plus or the minus sign between them. So when we see a plus minus sign between them, then we know that, okay, one term is ending here and this one is the next term. So this thing, these ones, plus, minus, addition, division, subtraction, whatever these are, we call them operators. These are the operators. And okay, so this one is the variable, and the numbers are called this one, which is without the variable, like it do not have any variable with it. We call them constants. 5 is a constant, 13 is a constant because this term cannot change. Like 5 will remain 5, 13 will remain 13, but this 2x, it will change depending on x. Like if we will change the x, then it will also change this term. So this is a variable, right? And the number with the variable is called the coefficient. And this whole thing, we call this an expression, and this is also an expression. They are connected by the relation of equality. So that's basically an equation. Okay, so there is a difference, a little bit of difference between an expression and an equation. Okay, so for expression, it's true for all the possible values of x. Let's say we had 2x plus 3. It do not have any, like whatever the x value that are allowed, you can just put them in, and it is true. It is not false for anything. You can put all the possible x values in it, and the expression is true. Okay, so the common key, like words that we can see that are used when we have an expression is like simplify the expression, expand the expression, factorize the expression. So these are the words like that where we use them for the expressions. Let's say 8x plus 5y minus 3x minus 5. So let's say it can be like simplify for this one. Simplify this, right? So simplify means like we have to combine the like terms. So let's say this is 8x minus 3x. We rewrite it and then just subtract. So it's like 5x plus 5y minus 5. And then we can take the 5 common. All right, so x plus y minus 1. So like that. So it's simplified, a little bit of factorized. So these are the things that we use for expressions. But this is an equation here. This have an equality sign there. Okay, so it's just true for some particular values. When it's an equation, it can be true for more than one value, but usually it's true for some particular values. Like for example, this one, we have 5x plus 4 equals to x. This one is true. We like combine we subtract the x, move the 4 to the other side. So 4x equals to negative 4. So x equals to. So this one is true only when the x is equals to negative 1. But this one is true for all the values of x and the y that are possible there that we can use. Okay, now there is, let's see some different types of equations that we normally see. There is many different types, but we'll just cover some common types of equations that we'll normally see. The first one is the linear equations that we did, I think, last week as well, or linear inequalities before last week. Each term involved in the linear equation is either a constant or a single variable or a product of a constant. Like y equals to mx plus c. Like each term have one variable. The power of variable is 1. Do you have any question, Anil?
I have a question.
Yes.
So, basically this is like combining like terms?
Combining like terms?
Or
Mm.
what operation is this?
Oh, this is the equations. These are the equations. They use the equal sign. So the left side of the expression, this left expression should be equals to the right expression. That's what equation means. Yeah. When we combine the terms, you can combine the terms on left side, you can combine the terms on right side, you can combine them on one side. But the main thing is this equal sign. So when we will see this equal sign, that means it's an equation. Like the linear equations that we just learned before, the equation of a line, y equals to mx plus c, right? So like that. So let's say it's like m is the slope and c is the y-intercept. Let's say we have something like this. So their graph, its graph looks like, let's say some graph, some random line. It looks like this. So that's this line is represented by this equation. Okay, it's true for some particular values of x and y. It's not true for all the values of x and y. Like for example, this one, 10x minus 80 is a equation. This is the equation in one variable, right? This one is an equation in two variables. 9x plus 6y minus 82 equals to 0. You see the power. The power of x is x, y, they're one. You will not see x, y term in this. In these kind of equations, you will not see xy term because its power is combined. Like you check the power combined, 1 plus 1, its power is 2, its second degree term. So all the terms are 1 degree, first degree terms, products with, they
So
are
in
just
this
product
case,
of,
that it says 9x plus 6y, what are you supposed to do?
oh, you like, it's the equation of line. Like you can convert it into line intercept form, or you can convert it into standard form of line like this, or like you could have it like, and then you can divide it by the 6. So y equals to 9. No, wait. So like this, and then you can then you can see that this equation is true only for some particular values of x. When you will input some particular value of x, you will get only some particular values of y for which these equations will be true. Next one is like this one is next thing after linear equations is the quadratic equations. These are the second degree terms. You see the x squared, it have a second degree term. The exponent is 2. They are like the parabolas. Let's say you might have seen the graph like this for parabolas, something like that. They are the x squared terms. So here the standard form of an quadratic equation is ax squared plus bx plus c. That's in one variable. You can have it in two variable, x squared plus xy plus y squared, like that. You can have like these equations. These are the equations, and this is the standard form for like that we normally use, ax squared plus bx plus c. So the for which we use the quadratic formula as well. So the coefficients, the a, b, and c, these are the coefficients, and the x and the y are the variables. These are just like the different types of like equations that you can encounter. Let's say then there is a radical equations, is a variable lying inside a square root symbol. It can be square root, cube root, or any root, right? It's not just the square root. Or you can say that the maximum exponent, oh, so like these are the radical ones. These are the radical ones, the square root of a plus 10 equals 26. Like these kind of equations where we have the square roots, we can have cubic roots, like those. So these are the radical equations that we have. And then exponential equations like the one that have the powers of something, like a to the power x equals to b, something like that. A is a constant, b is a constant, and x is a variable. So these kind of equations, because they are equal sign, these are the exponential equations, right? Like a to the power x is equals to 32. So what power of we can, like in this question, basically if they ask us to solve, we need to tell what power of 8 gives us 32, or let's say instead of 8, let's make it easy.
4.
Let's say I write it 2 to the no 8 to the power 4 is not 32. It's not,
No,
because
sorry,
8
I
to the
got
power 4
confused. I thought
means
you were talking about multiplication. Sorry, you're talking about square roots. My bad. I got confused.
no, it's the multiplications, but it's like 8 to the power x equals to 32, like that. So it means we need to know what power
Yeah,
of
like saying 8
x
to the power
should
2
be.
is 64.
Yes. So it's not 8 to the power of 2 actually, basically. Okay.
Yeah.
So it's like so we can rewrite it as like 2 to the power 3, that is 8.
8.
Yeah. And then 32. Right now we need to like see, now it's 2 to the power 3x equals to 32. Now we need to see what number here we put in x that will make it 32. So like 2 to the power 6 is 32, right?
Yep.
So we can have like x as 2 here. So like, but with the power of 2 to the power 6 is 32. So like that, we need to change it. So okay, then this is just an example as well. A rational equation. Rational equations are like in which you have the the powers like this, or you can have like 2x plus 3 over x equals to 7, something like that, or 7 over y, something like that. These are the rational expressions because these are the rational numbers, not real numbers. We don't have the powers which are exponents, or we have negative exponents and the exponents that are in the fractions. So these are the rational expressions because they include the rational numbers. These are the rational numbers instead of integers or polynomials. Okay, now we are moving on to functions. First we did was the equations. We talked about the equations, their basic notation and some types and some definitions for the equations. And now we are looking at the functions. What is a function? And then we will see its basic, it's kind of it's the part of the same topic that we was doing the first one, the equations and the functions, their notations and basic definition. So we will see what is a function and how we can see if something is a function or not, and what is the criteria for a function, what is its definition. So let's start with the first. A function is a process or associate each element A of a non-empty set A at least a single element B of another non-empty set B. So what we need is, first of all, to make a function, we need two sets. We need two sets, A and set B. We need two sets. The function is kind of a machine which take the inputs from the set A. Let's say this is f, the function. It takes the input from the set A. It processes it, whatever it do, whatever the machine do is, whatever its function, it do that, and then it gives the result from something in the set B. So that's what basically it do. So and then we have some criteria for the function that we see next, that which sets or which things make it a function. So a relation f, so it's a relation between A and B, the two sets. F is a relation, it's a relation between A and B, right? It's a relation between A and B. So the set of A is this from where we are taking the inputs is the domain,
And the range.
and the set outputs is like it have like people use it different names. They can sometimes call it codomain, they can call it range, or they can also use the word image. So these are all the words for the range, like range, codomain, and image. This is the set for outputs. Okay, so let's say how we write like function AB, the set AB, such that for all A that belongs to the small a are the elements, that belongs to this set A, input set, and the B is the member of this set. B belongs to this set, this bigger B set. So like the B are the members that belongs to set B. So it takes one input and map it. You can say map it, you can say image it. A function is also called a map. A function is also called a map. It maps an input to an output. It, you can say, and it gives, you can, the words can say that it gives you an image of a pre-image. The things that are in the domain are called pre-image as well. Okay, so when a relation is a function, a relation is said to be a function if every element of set A has one and only one image in set B. Let's say we have three things here, one, two, let's say 1, 2, 3, and there is A, B, C, D, E, like this. The function, what does it? The function is, I decide the rule that 1 will the A, 2 will the B. If I input the 3, I will get the C. All right. So now I know. Let's say I have made a machine. Whenever I press 1, the answer I get is A. When I press 2, the answer is B. Whenever I press 3, the answer is C. So it's a well defined rule. I have a rule. Whenever I will press 3, I will get C. But let's say what happen is this 3 also goes on to D. Okay, now what has this machine do? One time I press the 3, it gives me the answer as C. Next time I press the D or 3, it gives me the answer as D. Let's say this is our coffee machine, all right? So these are the different type 3 buttons, and these are the different type of coffees. So let's say one time you press the 3 and you get something, let's say cold coffee, and next time you press the same button 3 on the machine and you get cappuccino, something like that. Okay, you will never buy that machine that do everything with its own will. You will want something that gives you one specific output, unique output. Like once if you press one input, you get one output every time, the same. So one input cannot go onto more than one outputs. Okay, like it's not like if we write it in set notation or in table form. Let's say if I write it in like this, then 1 A, it's not possible that 1 gives me A and then 1 also gives me B. That's not a function. This is not a function. This is a relation, but this relation is not a function. And another thing for the domain, like for the function, is all the elements that are the member of that set A, the domain, they should, if we input them, we should get some output for it. It's not like that we leave the 3 here and we don't know. The 3 is here in this set, but it's not mapped on any output. It's not possible. Then it's not a function either, because we don't know that what will happen, like where this 3 goes to, on which number this 3 will goes to if we press the 3, because it have no like this input, it's an input for it, but it don't give any output. So even then, in that case, it's not a function. So all the input elements should give us an answer, which is one answer for one input. But it's okay if we have more than one answer for different outputs. Let's say like this. Let's say we have make a machine, we make a function which tells us the age, which tells us the age of the students, right? When we enter the name, all right? So let's say here they ask you enter name, okay? And it processes it and it gives you the age out. You press, you enter your name, enter your student's name. Let's say you enter your one student name and you get, like, enter your student name A, you get the age 13. You enter the student name B, you get the age 14. But at the same time, you get the age 14, 16, 18. How you will know that? What is the age of the student B if it's giving you more than one answer? then it's not a machine, it's not a function, there's no set rule for it. Because if there would be a set rule, then there will be only one answer for each input. But it's okay that more than 2 students have the same age. Let's say there is 10 students in the class that have the same age, 14. That's okay, that's completely fine, it makes sense. Different students can have same age, but one student cannot have multiple ages at the same time. So the function a to b, okay, so this is just everything that I explained here. Okay, so they're just telling us now these are a function in maths can be represented as the set of ordered pairs like a, b, or x, y. The x are the inputs and outputs. We can represent the function in this form. We can write the function in arrow form from a to b. That's the arrow diagram. We can use the table like before. Let's say we have the function x squared. The function is f of x equals to x squared. This is a general notation that we use for function. Let's say we can use it here. This is x, this is y. So when x is 1, we get y as 1. When x is 0, y as 0. When x is 2, is 4 because we are doing the squares. When x is 3, y is 9. So like these. So we can have table form. Even we can have the graphical form. Let's say this one. It have a graph x squared like this. We can represent the function by the graph, the table, by the arrow diagram, by this notations, right? Like that. So f of x equals to x squared. In the general manner, to represent a function, it is said as f of this thing is read as f of x equals to x squared. Okay, this is represented as f. You can also write it in like this way, the first set notation with the ordered pairs. Okay, the domain for this set is 1, 2, 3. The range for this set is 1, 4, 9. This is just the same diagram that we used before. It's also okay if there is some free elements in the range. It's not compulsory that whole range is covered, but the whole domain should be covered. And let's say there's one more thing that is left. Let's say if we have a graph of any random function. Let's say I have a function like this. How we can decide if it is a function or not. To do that, what you do is you just imagine in your mind the vertical lines over the graph. You imagine the vertical lines over the graph. If the lines at all the place, everywhere where you can think of it, never cross the graph twice. If the lines never cross the graph twice, then it's a function. It's called horizontal line test. Oh, sorry, vertical line test, my bad. Vertical line test. If the vertical line only cross the graph at once, then it's a function. Let's say I have a graph which looks like this. That's it. Looks like that. Now if you see, if I draw the vertical lines on it, okay, there's no problem here. It's not crossing, not crossing, not crossing. But as I cross it here, you see it crossing the graph at 2 points. The x value is the input. This is the x. These are the y values. You see one x value corresponds to 2 y values. So then this curve is not the graph of any function. It's not the graph of a function. It can be graph of anything, but it's not the graph of the function. So this is the vertical line test. If you have given a graph, you can just draw the vertical line and you can see if the vertical line crosses the graph more than once, then it's not a function. Okay, so now again, like these are some types of the functions. Okay, So these ones are like kind of a little different than the types of the equation. Okay, but the function a to b is said to be 1 to 1. It's a 1 to 1 function, or it's called injective function if the image of distinct elements of a under f are distinct. Like the images are the range, the element of range. If there is one element from the domain that joins with one element from the range, only one, and distinct elements, then it's a 1 to 1, like the first one. You see, one element from the domain joins with one element of the range. One element of like range, domain, range. So this is 1 to 1. For one element of input, there is one element of output. Then we have the next one is that we have is 1 to many. 1 to many. Oh, okay, I can explain from there. Let's say many. So this one is many to 1. The next one that we have here is many to 1 means the multiple input values, the multiple values from the input, like say 1, 2, like these two values, a and b, are joining one element in the
So they belong
range.
to X.
So this is
They
yes,
belong to X.
no, it's not like belongs to. Belongs to does not mean like that. Let's say this is the set A, this is the set B. Belongs to means that the small a, it belongs to the set A. Like it is the member of this family. It is the member of this set. That's what it means, belongs to. This one is maps. A maps to B, or oh sorry, not B, like let's say X. A maps to X, or you can say X is the image of A under the function f of x. Let's say this is a function f of x that we have here, a function. So we can say x is the image of A, or we can say A maps to X. That's what we use the words for this. Belongs to means that they are the member of that set. So the next one is,
So basically they're just connected.
sorry, what?
In many to 1, A is connected to X, right?
A, the correct word that you want to say is A maps to X. A maps to X. Or you can say X is the image of A, or you can say A goes to X. So these ones are the functions. 1 to 1 is a function, many to 1 is a function. They work for it, all right? And then these are the non-function, like 1 to many. Obviously, one input cannot go to multiple output. We already saw this, that 1 to many is not a kind of a function. This is not a function. Or many to many, like many to many, it's also not
A
the
function.
function. So now let's look here. Now look here as well. So now let's see here. So first we saw that 1 to 1, the word for 1 to 1 is also called injective. Okay, if the images of a distinct element of A under F are distinct for every AB in A, like A, B, they are from the set A inputs. F of A, F is a function, we apply the function to the A, and then it should be equals to F of B if F of A and F of B, there is two inputs, A and B. A and B, two inputs are there. We applied the function and their answers are equal. Okay, the f of A is equals to f of B. It implies that the A must be equal to B. Then it's a 1-to-1. 1-to-1 means if the answer of two inputs is equal, it means those inputs were the same, they were equal. That's what the 1-to-1 means. Otherwise it is many to one, right? Otherwise it can be many to one. Okay. The next thing is a function f a to b is said to be onto. Onto means it like covers, it is onto the b, like it covers the whole domain, whole range, whole element of range. There is no free element in the range. There is no free element in the range. Let's say we have 1, 2, 3. Let's say this is a b.
So it's a function.
Okay, one. Yes, it's a function and it is a onto function. Onto function. Onto means this covers this whole range. If the whole of the range is covered and there is no free element there left, then it's a onto. Okay, or you can say that for every element in B in the range, there is some element in the A that goes to that element in the B. Okay, so then another word for okay, then if something is onto and 1-to-1, if a function is onto and 1-to-1, okay, if 1-to-1 and onto are bijective, the onto functions are also called the bijective, then f is like it's both, okay. So like if a function is 1-to-1 and onto, then it's called bijective. So it's a bijective function if it is 1-to-1 and onto. Okay, so now we are moving to our next topic, which is composite functions. And so this is our second topic in the list, composite function. And
You missed a P right there. It says composite function.
sorry,
It says composite function right up there.
it's bad, it's spelling mistake, sorry. Thank you for correcting. It's composite functions. I missed the P, sorry. Composite functions. Okay, so now composite function means, like, let's say we have seen that we can add two functions, we can subtract two functions, we multiply them, we divide them. Now this is something which we're not multiplying, we're not dividing, or we are not adding or subtracting them, but what we are doing is it's like let's say it's like kind of a factory. Okay, there's different machines. Let's say we have, this is machine F, this is the input where you put something into the input. This is the machine, like inputs are X, right? You put the inputs in it, X. You put the inputs there. This is the machine, the first machine, right? What does it do? It takes the input, right? Whatever you had. Let's say we are making something, all right? We are cooking, or it's like a baking machine or something. Let's say it takes the input, it takes some grains or whatever, it grinds it, makes some flour or something, whatever. Then it gives us an output, right? These are the outputs for that inputs. Right? This is the box of outputs. We put in an input into the first function, it gives an, now let's say what we do is we take this output and feed it to the next machine. Now what we do is we feed it to the next machine, right? The outputs of the first machine, outputs of the first function, we feed them to the second function. That is what is kind of the composite function, right? So whatever the answers it gets us, like whatever the answers it will give us out, that will be the final answers. So okay, so let A to B, and G, B to C be two functions. We have two functions, okay? F and G. Then the composition of F and G is denoted as f of G, okay? And then the variable, whatever the variable we have, if the variable is X, we write it as X, or you can write it as f of G. This is not O, but a small circle like that, which is read as f of, oh, so there's also one, just one, f of G. So we read at f of G, it's read as like f, the input of f is the function G, okay, and then X belongs to A, whatever the set is, whatever the domain is, X belongs to the inputs. Okay, let's see some example, and then we'll also see quickly a little bit of, if we get the time, for the domain and range for this. So let's say we have a function here. Let us consider an example of two functions, f of x and g of x. So f of x is x plus 1. This is our first function, which is x plus 1. And the second function is g of x is x squared. Then f of g of x, like f of g, which we are trying to find, is f of g of x. That's how we will write it. So what is the g of x now? The g of x is equals to x squared. So what you do, you plug in the value for g of x, which is x squared. Now the input is not x, the input is x squared for the x. Okay, so what was the x? What is the function f? This is the function f here. F of x equals to x plus 1. So what we do here, now we have f of x squared, that will be x squared plus 1, because we will replace the x by the x squared. So this is the that's what we get for f of g of x. This is the one of the composition, f of g of x. All right, so f of g of x is this one here. Now what we do is, we do the, now next one is we do g of f of x. Like now we take the, now we are doing g of f of x here, g of f of x. Now what we're doing, we are first feeding the x to the f, the function f, we get its own output, and then we feed it to the g, like this, g of f of x here. See, g of f of x here. Okay, so now then the g of f of x is equals to, what is the f of x? You put that here, x plus 1 here. And then you use the function x plus 1 squared, because the g of x is x squared. Now it will be x plus 1 squared, which will become x squared plus 2x plus 1. Okay? So you can see that the f of g of x and g of f of x, they are different. So you can see that f of g is not the same as g of x. You can also see it in, you can think in real world scenario, that if you have two machines, you first put your input into first machine and you do something, and then you put it into second machine and it do something different. You will not get the same result if you put the same thing into the second machine first and then put it back into the first machine, right? So it's the same like the functions. And also one more thing about the domain and the range is, also let's say when we do the composition function, we get x squared plus 1, but we will not see the domain of the answer. We will not see the domain of the answer. We will see the domain of the original functions, f of x and g of x, all right? Because let's say we have two machines, all right? We are making something. So the first machine cannot take sugar. Although the second machine can take the sugar in, but the first machine cannot. First function machine cannot take the sugar. So if you cannot put the sugar into the first machine, then whatever the output you will get, that will not have sugar in it. Because you feed the output from the first machine, so second machine will never get the sugar as well. Although you can put in it, it's allowed to put in into the second machine, but since you are putting the input into the second machines that you get from the first one, and the first one cannot have sugar, so you cannot put the sugar into the second one. So you look at the original functions for the domain, right? Let's say I have two functions, f of x equals to square root of x, and g of x equals to x squared. G of x equals to x squared. Although the second function x squared, it can take all the values, but this one, it cannot take the negative values, right? So g of f of x, the domain for this one is only when x is greater than or equal to 0. It cannot take negative values. Although x squared can take negative values, but the other one that is going into the input, that cannot have the negative values. So you cannot take the negative values for this one. So you take the domain depending on what you are giving it as input. You look at that function, the input function. You look at the domain of that, and then you solve it, and then at the end you again look at the domain of the final answer. Okay, now their next thing is an inverse function. Inverse function is like it's not possible to get the inverse of every function. The inverse of only one-to-one functions exist. If the function is one-to-one, then you can find its inverse. And the rule is that if you do f of g of x, the answer should be x. And g of f of x, the answer should be x. Okay? Inverse functions. No, there's nothing like outverse function. No, it's the inverse function. Inverse means the opposite, like it cancels it out. Okay, it's not in, it does not mean like in means something inside it. It's not like that.
Yeah, like
in
saying input, and outburst is like saying output.
Not, yeah, yes, like it's like they have the same like inverse function, like they cancel out each other. Basically the concept is, let's say x squared and square root of x, they are kind of, for some values they are the inverse functions. All right, let's say if you have because like whatever you like x, whatever the x squared did, the square root of x, undo it. Let's say I put in 2 into the x squared, I get the answer as 4. Now if I will do the square root of 4, I will get back 2. So you see, whatever the x squared did,
You
the
inversed
square root
it.
of x reversed it. It put it back. So they are the inverse function. They cancel out the effect of each other. So the criteria is that how we can check if two functions are inverse. We do the composition of those functions, f of g of x and g of f of x, and the answer for both of them should be x. Let's say, okay, I have only 10 minutes, so I'm just skipping this one, and let's do the next example here. Let's say I have two functions, f of x and g of x. Now I want to check if they are inverse or not, if they are inverse functions of each other or not. So what we do is we do f of g of x, right? So it means f of g of x, like that. And what is f of g of x? Function that goes here, cube root of x minus 2. And now we substitute it into the x. The input will go here. So that will be equals to cube root of x minus 2 to the power 3 plus 2. You do the cube root cancels out, x minus 2 plus 2. So you got x. Okay, so f of x is equals to f of g of x is equals to x. We got the first condition true. Now we need to check is g of f of x. So that is g, you write it like this, f of x. So what is the f of x? The input, x of f of x is equals to x cube plus 2, like that. Then you take the g here. you substitute in the x here, because when the input was x, it was x there. Now the input is x cubed plus 2, so it should be x cubed plus 2 here. We replace the x by the x cubed plus 2. So you see x cubed plus 2 minus 2, which cancels out, and then cube root of x cube is x. So yes, we get in this both scenarios, we get that. So these two are the inverse functions. And there is one more thing about the inverse functions is, let's say if we graph them, let's say the logarithmic function, log functions, and exponential functions. They are log and exponential. They are also the inverse of each other. Log and exponents are also the inverse of each other. Let's say we have some, so if we have the line y equals to x, let's say this is the line y equals to x. So let's say the exponential function, we have 2 to the power x, right? This is an exponential function, which looks like something like this. So this line will mirror it. This line will exactly mirror it, and the logarithmic function will look like, the logarithmic function will look like, it will look exactly mirror, like although my drawing will not look like exactly like a mirror image, but you can see that this line in the middle behaves like a mirror. So when you graph the inverse functions, they look like this line behaves like a mirror in the middle, y equals to x. Okay, so now the last thing is, this is the third one, last topic for now. So the transformation of graphs. Let's say we have a graph and we want to transform it. We want to move it up, down, left, right, do something, flip it, reflect it, shrink it, expand it. So let's start from the first one. Let's say the g of x is, we have f of x minus h plus k, right? So this h here, it moves it horizontally. The h moves it horizontally. If this one, like x minus h, okay, so if this x here is, if this h is let's say a negative number, let's say x minus 2, like this, f of x minus 2 plus something, right? So then this, if h is greater than 0, then it moves that many units to the right. Okay, it moves it right. If h is less than 0, it moves to the left. Let's say if this k is greater than 0, k is greater than 0, then it moves up that many units, and if that k is less than 0, then it moves that many units down, right? Vertical units, this k here. So then g of x is minus f of x, it's reflected in the x-axis. If you multiply the function by a negative, it's reflected over the x-axis. Let's say we have the function f of x equals to x squared. So if we multiply it with the negative, so negative of f of x will be equals to negative x squared. So the f of x looks like this, but the negative of f of x will look like this. It will be reflected over the x-axis. So, but if you put the negative inside, like you replace the x by the negative x, then it will be reflected across the y-axis. Let's say the function was like, let's say the function was like this, then it will be reflected and it will become reflected over the y-axis, something like that, the graph. Then this is c times f of x. If you multiply the function, the graph of the function, by some number c, and c is greater than 1, then its vertical stretch by the factor of c, like it's being stretched vertically. Like let's say before, if it was like this much vertically, then it will be in the same time it will be vertically stretched like this. This is a vertical stretch from this way to this way, and if you go from down to up, like from down to up, that's a vertical shrink. If it is in between, if you multiply the function or the graph by something which is in between 0 and 1, let's say 1/2, 1/3, then it's a shrink. And at the end here, it's k times x. If you multiply input, the inside input, by some number k, then it's a horizontal stretch by the factor of 1/k. If the k is in between 0 and 1, let's say if k is 1/2, you multiply the x by the 1/2, then it's a vertical stretch. It's opposite in case of horizontal. If you multiply by a fraction, a number in between 0 to 1, and if you multiply it with number which is k greater than 1, then it's a vertical shrink by the factor of 1/k. It's not vertical shrink or vertical stretch by the factor of k, but instead it's the vertical shrink and vertical stretch by the factor of 1/k. Let me show you some example actual on this. This is a graphing calculator, Desmos, that you can even use for yourself. Let's say my function is f of x is equals to square root of, I'm just writing it power 1/2. Yeah, that's what the square root means. Yeah, like f of x is square root of x. Now I want to, okay, just tell me, every one of you, just tell me what should I do with it. You want to move it right, left, up, down? Okay, first of all, how many units should we move it right? If we want to move it right, what we need to do? We need to subtract. Let's say I subtract 3. You see, it moved 3 units right. Okay, I subtracted 3 in f of x. It moved 3 units to the right. Let's say I want to move it 2 units up. So I need to add 2 outside. You see, it moved up 3 right, 2 up. Okay. Let's say we want to reflect it across the y-axis. Let's multiply it with the, then we have to multiply the whole thing with the negative, right? Let's see here. You see, it's not the actual reflection. If we want to reflect it, then what we need to do is we need to take another step and reflect the g, because now our function is g of x. Now we need to write like h of x, a new function, is equals to the reflection of the function g of x across the x-axis. See, like this. If we want to reflect it across the y-axis, then what we do is we put the negative inside. You see, it's reflected across the y-axis. We can also stretch it vertical, like let's say we shrink it vertically. If I put the 5 here, it's a shrink. See, the x values, if you will see, it's shrinked, the x values. If I want to stretch it by x, let's say 1/5. Oh, you can't even see it now because it's stretched and it's here. See? So like that, x values are stretched. Now whatever the answer was at like 4, now the same answer is at 16 or 20. It's stretched on the x-axis. Let's just like we stretch it vertically. Let's say if I multiply it with 3, you see it's vertically stretched. Before it was covering this much portion vertically in this values of x. Now it's covering this much portion of y. So it's the vertically stretched. If we divide it by some number, let's say 1/3, or let's say 1/3. Oh, wait. Okay, you see now the x, now on the same time in the same area where it was taking this much space on the y-axis, now it's just taking a dot, like very small space on the y-axis. So it's vertically shrink. All right. Okay, so you can try yourself, like write any function, try to move it right, left, up, down. This is a website that you can use. It's Desmos. Okay, so you can use it. You can write your own function on graph, and then you can just play with it, move it up, down, right, left, do the translation, reflection. You can do combinations of it. Is it okay? So is it okay with everyone?
Yes, teacher.
It's clear? You understand?
Yes, teacher.
Okay, excellent, guys.
All right. Okay.
Okay, so excellent class. Thank you so much. Guys, thank you for being here. Wonderful days to all of you. Prepare for next class. Okay. Have a wonderful day, guys. And teachers up. Enjoy the rest of the day. Thank you so much. And bye-bye.
Bye, teacher.
Bye, Daniel, Paul. Bye, Mark, Matthew, Rick. Bye-bye.